Hello, welcome to my workshop on how to create a searchable Django web application using Elastic App Search. Today, I'm going to be introducing Elastic App Search, the service, and talk about how we can take advantage of all of App Search's features to create positive search experiences. A little bit about myself. I'm Seth Larson. I've been a software engineer at Elastic for a little over a year now. I'm primarily focused on creating and maintaining Python API clients for all the different services that Elastic creates, like Elasticsearch and Enterprise Search and more. Outside of work, I contribute to open source, specifically Python networking and HTTP libraries like urlib3 and requests. You can find me on GitHub and elsewhere as @SethMLarson. So this workshop comes with a handful of code examples that you can try yourself, along with a small Django application that uses app search in a bunch of different ways that are all going to be discussed in this presentation. And if you want to follow along live with the examples, you can do that. However, it's totally fine to come back to them after the presentation as well. For this presentation, I'll be using the App Search UI for most of it, but the code examples themselves replicate what is done in the UI with the App Search APIs. All the code for this presentation is available on GitHub, and the repository is listed on the slide. And with that all out of the way, let's get started. So typically when you think of Elastic, the company, you think of Elasticsearch, which is a behemoth in the search solution space. Something that Elastic engineering has been focusing on for the past few years now is that now that we have all of this amazing technology in Elasticsearch, what can we do to provide a more curated and specialized experience to developers using Elasticsearch and the rest of the Elastic stack? So today's workshop is focusing on a service that you may not have heard of before called Elastic App Search. We're going to learn about the use case for App Search and how we can integrate that into web applications in Python. The Elastic stack is a pretty big place with lots of different solutions and products. So for the sake of being able to find documentation and search for things and answers in your search solution of choice, I want to clarify where App Search is in the Elastic stack. App Search is a product within the broader enterprise search solution, along with another great product called Workplace Search. App Search, like all of the solutions, is built on the stack, specifically Elasticsearch. So when you go to download and actually run an executable, you'll be running something called Enterprise Search, as both the App Search and Workplace Search products are combined into a single service that have their own UIs. This means if you're using one of them, it may be a good idea to check out the other to see if it's also useful to you or your team, because they're bundled together automatically. App Search can be really summed up with a single line: advanced search made simple. One of the great things about Elasticsearch is that as a developer, there are thousands of options available to you on how to make searching, indexing, and storing data behave exactly the way that you want. But that upside can also be a downside if you really just want your service to be searchable without having to do tons of hand tuning by yourself. So instead, maybe what you really want is those thousands of options to be set to really great defaults, and then for the handful of options that really matter the most to your data and service to be really easily configurable. App Search also comes with features that aren't provided by Elasticsearch that close the feedback loop when it comes to building and maintaining a search experience. Features like analytics to show what users are searching for, what they're clicking on, and where your search experience can be improved. And then tuning, which allows you to tweak searches on the fly without having to make any modifications to your code. These are features that you'd either have to roll your own or supplement elsewhere if you're using Elasticsearch by itself instead of App Search. The best way to think about App Search is the heart of a search bar in your web application. App Search has two conceptual units: engines and documents. Documents are data that describes something that you want to be a result of a search made by a user. And then engines are a collection of documents along with settings about how to interpret and rank the data within a document. The way an engine interprets the data within documents is called the schema. Search settings determine how each document is scored when a search is executed. And then finally, analytics is data about how the engine searches are performing from a search experience point of view. All the data and settings for App Search are inevitably indexed and stored within Elasticsearch, but this detail is completely transparent from an App Search API perspective, All you need to think about are documents and engines. So what types of data is App Search for? App Search supports all of the standard create, update, and delete operations that you'd expect from a schemaless data store for documents, but also for engine settings themselves too. App Search is built so you don't have to worry about the complexities of doing data migrations or reindexing data. Simply make the changes that you want to see, and they'll be available with zero search downtime as soon as processing completes. App Search is much more like a NoSQL database than a relational database. There's no built-in way to have relationships between documents or engines. Instead, data should be mostly flat and should stand alone as a search result. Because of this, a typical use case for App Search will be as a companion data store optimized for search, opposed to your primary data store. But there are certainly cases where you don't need ACID compliance, and then maybe this can become an option for you. My recommendation, though, is to go into thinking of App Search as a search service rather than a data storage service. Finally, the data within App Search should always be relevant. If there's data in App Search, it means that it can show up in your search bar. If you're indexing tons and tons of data that really is mostly relevant right now, like logs, events, and time series data, then you likely will want to use Elasticsearch directly instead. Elasticsearch provides many more options that are specialized for this use case, like data tiers, searchable snapshots, and async search that really don't fit in App Search's model of treating all data within the engine the same. All right, so we've introduced App Search a bit. Now let's talk about how we can use App Search from Python. There's a newly developed open source client for all enterprise search APIs, including both App Search and Workplace Search. The package is called Elastic Enterprise Search on the Python package index, and you can install it with pip as shown. The source code is available on GitHub, and the documentation for the client can be found on the Elastic website, elastic.co, under guides. This client was recently upgraded from beta to generally available in February with Elastic Stack 7.11. We welcome and celebrate contributions from the community. If you decide to start contributing code or documentation, I recommend looking up the Elastic Contributor Program, where you can get swag and awards for contributing to Elastic projects. Engaging with the community is one of the most rewarding parts of my job, so I'm always happy to see new faces. I've also already seen some community-led projects being built using this new client, which is really exciting because this client has only been around for a relatively short amount of time. So I'm looking forward to what else will be built using this project. The client itself is mostly generated from an API specification. So new APIs are available right when the new version of Enterprise Search is released. Immediately from day one, you can use these new APIs available after you upgrade. The client is separated into two layers, the API layer and the transport layer. The API layer is mostly generated with a few additional service-specific behaviors and helpers for authentication. The transport layer is a separate component that was lifted from the popular Python Elasticsearch client, and so it's been used by a very wide set of use cases, and it's been proven to be effective in those use cases. The transport layer handles serializing native Python types like datetimes, decimals, lists, and dictionaries into bytes that are sent to the service via HTTP. So you don't have to do these transformations on your own. The transport layer is also very configurable for TLS, connection pooling, failover, and more depending on your use case. All right, so from here on out, we'll be needing a live instance of Enterprise Search to work with. There are a couple of options when it comes to starting an Enterprise Search instance that are covered in more detail in the workshop materials. The two options are either hosting an Enterprise Search instance in Elastic Cloud or starting your own self-hosted instance locally. Elastic Cloud is what I'll be using today to deploy an instance for all of the demonstrations in the App Search UI. The other option is to use Docker Compose to create an Enterprise and Elasticsearch instance locally. This Docker Compose config will start 2 instances with a trial license, so I don't recommend using this setup for anything beyond maybe integration testing. I'm going to quickly show how to create an Elastic Cloud instance and connect to it from the Python Enterprise Search client. So I'm currently on cloud.elastic.co. I've already created an Elastic Cloud account and I've logged in. This is the screen that you'd first see when logging into Elastic Cloud. You can see I already have a couple of deployments, but we're going to be creating a new deployment today. So we're going to select create deployment. And then we're going to select the enterprise search template as a good starting point. So then you can change your deployment settings like your cloud provider and the region. So I recommend setting these to be the same as where you're actually hosting your application. So if I hit expand, I can choose any cloud provider I want, as well as any region. And then always recommend using the latest version. So we're just going to go with the defaults here. US West and Google Cloud should be fine. And then we always have to choose a name for our deployment. I'm always just going to stick with the default. And if you have some more advanced configuration options, you can go here into customize. And here you can see like exactly what type of Elasticsearch instance and how many instances are going to be added, and also how many instances of enterprise search are going to be started. For today, I'm just going to go with the defaults. So I'm going to select create deployment. And right after I select create deployment, an instance will start provisioning. So that'll take a couple of minutes. You'll get the Elasticsearch credentials that are more useful if you're going to actually have like a real deployment as opposed to just a demo deployment that we're doing now. So for now, we don't really need these, but if you're actually going to be creating an Elasticsearch and enterprise search instance in production, you'll want to save these somewhere. So we're going to continue without downloading. And so this will take a few minutes. Just wait for that to provision. And then once it's done provisioning, we'll be back and we'll start using App Search. Okay, it's been a few minutes. And now that our deployment has provisioned, we're on our deployment settings page and we get access to the enterprise search instance. So let's launch it. And then from here, we can select either App Search or Workplace Search. Today, we're going to be selecting App Search. And then we're kind of put on an onboarding screen. We don't really need this because we're going to be actually going through the setup of our first engine manually. So we're going to skip onboarding. Okay, now that we're in the App Search service itself, we can actually go to the credentials screen. And here you'll see two bits of information that we want to be able to actually run our examples. So we have the API endpoint here, which is basically just the URL that our service is being hosted at. And there's a copy to clipboard button here. And then we also want the private key to be able to authenticate with the service. So there's a copy to clipboard button here. You're going to copy and paste both of these values into the URL and private key fields, respectively, within the config.yaml. And then after you have those values there, you should be able to run example number 1 and see a successful result. So while we're in the credentials screen, I'll explain quickly the difference between a private key and a search key. So a private key is essentially the read and write API key. It can do anything, so really should be protected and not shared. It can use all of the APIs, create and destroy things, all of that. The search key, on the other hand, is only capable of executing the search API, and so can actually be shared with users to make searches from the browser. For Python, however, this really doesn't matter that much because we're developing a web backend instead of a web front end. So for all of our examples, we'll be just using the private key. So this next section of the presentation corresponds with example number 2. So we're going to actually create our first engine in the UI and start indexing some documents. So you're going to go over to the engines page. And then we need to give our new engine a name. I'm going to use National Parks PyCon 2021. And then there's a selector over here for selecting the language of the text of all the documents within the engine. If you know what language it's going to be, you can select it here. So you can have all the standard languages. And then if you really don't know what the language is going to be for these documents, you can just keep it as universal. The only thing that really this changes is it makes the analysis for like language dependent text analysis a little bit better. So if you do know the language, it is useful to set it. And then we're going to create the engine. So now we have an empty engine. There's no documents in it. So there's a couple different ways that we can use to get documents into the engine. You can either copy paste JSON. So there's an example here. You can copy paste a literal JSON file into the engine and it'll index it. You can also upload a JSON file. So you can just drag and drop a JSON file in and it'll index all the documents. Or you could use a web crawler, which we'll actually talk about a lot more in the future in this presentation. So for now, we're actually just going to use upload a JSON file. So I'm going to go off screen and grab the data file, drop it in, hit continue, and then all of our documents should get indexed. It'll show all the different fields and documents that have been added. So right now we have 59. And then if I go and look at the documents actually in the engine, you can see they all have fields that we're expecting. So we have documents in the engine. Now we need to tell the engine how to interpret each field in the document by updating the engine schema. So let's open up the schema page. And you can see by default, all of the fields are actually being listed as type text. That's not correct. A lot of these need to be something else. So there's 4 field types that we have to choose from: text, number, date, and geolocation. So the text type is really useful for strings, both small and large, and it can also be used for enumeration values. The number type is used for integers and floating point values. The date type is used for both dates and date time values. And the geolocation type is used for geographic points of latitude and longitude. Notice that there isn't a Boolean type currently. I recommend treating Booleans similar to enums, and so it should be a text type. I'm going to set all the fields to the types that we would expect. So for area, we're going to set it to number. Established, we're going to set it to a date. Number of visitors, we're going to set to a number. And then location, we're going to set to a geolocation. So once we've done started setting them, we're going to hit confirm types. And then from there, the process will start of actually re-indexing our documents. So if you've ever updated an Elasticsearch mapping, you know that re-indexing data without downtime requires a bit of juggling, but AppSearch does it all transparently for you and then lets you know if it encounters any issues. So we've gotten documents into AppSearch using the UI and the APIs manually. Let's discuss now how a Django application should use AppSearch as a companion database and keep its primary data store and documents in AppSearch in sync with each other. There are a couple ways we can do this. The first way uses model signal receivers in Django. Basically, you set up receivers that re-index the model every time it's modified or deleted by Django. As long as updates to the database are all done through Django, this will keep your AppSearch documents up to date automatically. However, if you have modifications to the database outside of your Django application, those updates wouldn't be captured by AppSearch as they won't trigger a signal in Django. This implementation will make sure updates to your primary data store are immediately available within AppSearch, but has no mechanism for recovery if the two get out of sync. The second way is to regularly query your database for all models and update AppSearch using meta engines. Create a new engine every time the task is run, and then fill it with all the documents you expect to be in AppSearch, and then switch the meta engine alias to the newly created engine. This is a lot easier to reason about as you don't have to worry about individual operations failing. However, it means that your primary database and AppSearch will be out of sync between executions of the task. We'll talk about this approach more after talking generally how to transform a Django model into an AppSearch document. A document in AppSearch is essentially a flat JSON object. So we'll need to take our Django model, which potentially has complex types or relationships, and transform it into data that's relevant to AppSearch. The first thing to do is to determine what data AppSearch actually needs. If there's data that doesn't matter for searchability or filtering or sorting, then it doesn't need to be indexed in AppSearch. You can just ignore these fields. For every other field, it must be transformed into either a scalar value, like a string, integer, float, or an array of scalars. The serializer can handle transforming datetime objects into strings in the proper format for you. A couple important things to note are that the document should contain an ID, which can either be derived from the Django model itself, or you should store the ID for AppSearch that gets generated on the Django model. As I mentioned earlier, there are no Boolean types in AppSearch, so the World Heritage Site field, which is a Boolean field in Django, is turned into the string false in AppSearch. And finally, geolocations are latitude-longitude pairs in a string value. In this example, the latitude and longitude Django decimal fields are transformed into a single field location in AppSearch. A small note about time zones when it comes to datetime objects. This advice applies generally to working with datetime objects in Python, but it especially applies to working with app search. The datetime format that app search uses is RFC 3339, which requires time zone information on every datetime. This is great because it means that libraries, that smart people who actually know how time zones work, can do the right thing when it comes to datetime calculations. However, this means that we need to provide this information to app search for all of our datetime objects. To quote Python's very own time zone wizard, Paul Gansel, stop using UTC now and UTC from timestamp. UTC now and UTC from timestamp give date times where all of the values for year, day, and hours, etc., are in UTC time, but without the UTC time zone annotation applied. From RFC 3339, the recommendation is that a date time without a time zone should be assumed to be in the local time zone. And this is exactly what the app search client does, which works great in almost all cases, but this means that you're going to be getting bad values if you use the functions UTC now or UTC from timestamp with the app search client. I highly recommend checking out Python dateutil if you're working with datetimes in Python. Meta engines are nice to have when implementing the recurring indexing task. Basically, it provides an unchanging name which searches can be sent to where the actual data lives in different engines. A meta engine's documents are stored in engines called source engines. Source engines can be added and removed from the meta engine without interrupting the search experience. Meta engines are a Platinum license feature, so you'll have to access them on Elastic Cloud, or if you have a Platinum license on a self-managed instance. To implement the indexing task that uses meta engines, the task should create a new engine and fill it with the desired documents and schema. Then make an update to the meta engine to set the newly created engine as the only source engine and delete all the other source engines. This should result in all of the updates and deletes from the primary data store to be captured in app search. If you're looking for the best of both worlds, for fault tolerance and for your primary data store and app search to be up to date really quickly, it's possible to implement both the signals and the task to work together. All right, now that we've talked about more involved ways to get data into app search, let's talk about a much less involved method that requires very little code on the Python side with app search's web crawler feature. Web crawler takes a web URL like https www.example.com and crawls all pages that it can discover from the entry point domain, grabs the relevant information and metadata from the page, and then indexes all of that data into app search. This approach works really great because it means that your website becomes completely searchable with basically zero effort. You're hopefully already going through the process of making your website crawlable, so you'll get searchability automatically after that. The web crawler feature, as of Elasticstack 7.12, is in beta. However, general availability is coming soon. One of the downsides of this approach is it focuses completely on searching for pages rather than anything else. But for a lot of use cases, this is actually exactly what you want. Another downside is that you currently don't get a lot of control over what your document's format is or structure, but that'll be coming soon. There's only a few things that you'll need to configure for your website to make the app search web crawler effective. You'll need to figure out all of your entry points, which should be places where all of your desired content can be discovered from via links. Then you'll have to create a URL path filter so that you don't ingest any pages that aren't intended to be searchable. The other thing that you'll need to do for your web application is to implement a few SEO and crawlability best practices that really you should implement whether or not you're using the web crawler. Having a sitemap.xml file and a robots.txt file are recommended to make your website much easier to crawl. It's also recommended to fill out the title, meta description, and to set no follow on links that you don't want crawlers to follow on the page. Let's take a look at what the web crawler looks like in action. So I'm going to create a brand new engine meant to make Elastic blog posts searchable. I hit create new engine. I'm going to call it Elastic blog. So instead of manually indexing via the API, we're going to use the web crawler instead. We have to add our domain. It's elastic.co. Click setup domain. And then we have to configure an entry point. So right now the entry point is set to elastic.co. We're going to change that to elastic.co/blog. That means that the web crawler will start here when it's looking for new documents. Then we're going to update the crawl rules. So the default crawl rule is to accept any page, as you can see here. But we only want pages that are under /blog. So let's create a new default rule that captures all the paths and disallows them. Select add crawl rule, policy of disallow. Rule is regular expression, and we're going to do capture all. Now we're going to add another rule on top of that that accepts paths that begin with /blog. So we're going to add another crawl rule, policy of allow, begins with /blog. And we're going to hit save. So this is a pretty common construction when it comes to configuring your crawl rules. So after our rules are set up, we now click the button to start a crawl. And then after some time, some documents will start showing up in our engine. So let's go look at documents. All right, so I waited for a second, and now there are actually some documents in our engine. So if we actually look at the document itself, you can see that there's actually tons of information from the page on each individual document, not just the content, but also lots of metadata as well. So this allows the actual search engine to use everything that was on the page to provide really good search results. And then in the future, if the page were to be updated later, the crawler would eventually re-index that page and update the corresponding document within app search. So I'm going to let this run for a little bit longer to get a good amount of documents, and then I'm going to show off the final results. Okay, so I've waited for a minute, and we now have a couple hundred documents in our engine. Let's do a search for blog posts about the new frozen data tier and see what comes up. If I hit frozen tier and search, you can see here's a result. Let's go ahead and give that a click. And this looks like a pretty good result. So this is kind of what the experience would be like for a user that's searching an index that has used the web crawler to index documents. Using the web crawler, we were able to build a search experience without having to do much from the Django or Python side at all. And we didn't really have to worry about how our website will stay in sync with app search. Speaking of searchable, now that we know how to load data into app search, let's talk about search. The best part about searching with app search is that for the most part, you're sending the text that a user typed into a search bar to the app search instance without much else. You receive back some results and some metadata about the engine, pagination, and a request ID. Remember this request ID for later on. The results are automatically sorted by search score, but can be sorted on other metrics as well. In addition to the query text, you can add filters or submit facets to get values like what is the average number of visitors for all parks? Think of facets like you do aggregations in Elasticsearch. That's really all there is to say for search from an API perspective. Query suggestions are very close to the same as search. However, the API is meant to give fast feedback to users about potential queries that have high scoring results. The implementation for this uses Elasticsearch's best fields match instead of the cross fields match to achieve better performance while still recommending good results. If you're interested in result suggestions instead of query suggestions, I recommend using the search API directly with a partial query. So remember when I talked about the two different types of API keys, private keys and search keys? There's a type of search key that works a lot like a pre-signed API request if you've ever used one of those with a cloud service. Basically, you use a private key to create a new API key that you can hand to users directly that has limited access and abilities compared to a full search key. You can limit which fields the user can see, which fields can be used for search, and more. Signed search keys likely won't be used by the Python client to make requests because search keys are more for front-end languages like JavaScript, but you can still generate them from the Python client with the create signed search key API. So this isn't a JavaScript workshop. However, front-end is a big part of web applications. App Search provides a great place to start when building a front-end search experience with the reference UI. This lets you immediately have a React boilerplate for search that works with App Search. The example Django application has this configured so you can check out how it works. And because the code is all open source, you can take it and modify it to your heart's content. All right, that's all there is to know about search. But once you've got users searching and results coming back, App Search also comes out of the box with a bunch of tools that'll help you make your search experience even better for your users. These tools come in the form of search analytics. A lot of these analytics show you what your users are searching for and how often those results end with a user actually clicking on the result. You can subdivide all of these analytics by a tag that can be set on many different APIs, so you can see which source of analytics is reporting a certain way. For instance, if you had multiple applications using the same engine, you'd want 2 different tags at least. A lot of these analytics come for free with no changes, but the analytics regarding clicks themselves need just one more change to actually report the clicks back to App Search. Remember earlier I mentioned we'd be using the meta.requestID field? Well, that time has come. Take the value that you received for meta.requestID along with the document ID that the user clicked on and pass those as parameters to the log click-through API. This automatically populates the clicks per query and queries without clicks analytics in App Search. So what do we do with all of these analytics from App Search? We can take them and then try to make our users' search experience better. The 2 indicators of negative search experiences are the no results for query and no clicks for query analytics. Seeing a query that's being searched for a lot without any click or results means that a lot of your users are having a negative search experience, and that's something that you'll want to fix if possible. The solution is tuning your engine to make those queries return better results and hopefully help users find what they're looking for. If a query isn't getting any results back, it may be that the query is using a synonym for a keyword that's not actually in the documents themselves. It could also be that the query is a common phrase that makes sense to humans, but likely won't be in the document itself. Think along the lines of biggest park. If it's not mentioned in the description of the App Search document, then App Search won't know to rank the largest park at the top of the results. So now that we know where our user's search experience isn't the greatest, let's look at all the ways that App Search lets you improve the search experience via tuning. There are 3 ways to tune your search results in App Search: relevance tuning, curations, and synonyms. Relevance tuning is changing how much each individual field contributes to a document score when it's searched for. This can come in the form of a weight multiplier for text relevance, or in the form of boosts, which uses a formula to calculate how much score should be added based on the field. Curations allow you to complete control over the results for a given query or queries. If a user searches for the phrase biggest park, you can have the pre-calculated biggest park document always show up as the #1 result, and then manually hide all of the smallest parks, so no matter what, they won't show up. Synonyms impact how text search works by marking 2 different terms as having the same value. For example, people often say buffalo to refer to the American bison for US state parks. So if a user were to search for buffalo, they'd be surprised to find 0 results. But adding the synonym for buffalo is equal to bison, the user will receive all the results they intended seamlessly. Let's see how we can configure all of these tuning methods by hand in the App Search UI. So here we are again in the App Search UI. To configure each field's relevance, we open the Relevance Tuning tab. We can see within this tab, we have a feature called the Query Tester, which allows you to see in real time as you make changes to your document scoring, which sorts of documents would show up if a user were to issue a given query. Relevance tuning is also a really great place to go right after you've added new documents or new fields to make sure that each field is configured how you want. Remember back when I said to use text fields for enums and booleans? Well, if we search for the word true, we can see based on the field highlighting that the World Heritage Site true is getting text searched. We don't really want that to happen. That's not how we want this field to behave. Instead, we really want the field only to be available as a filter. So to fix this, let's make the field not text searchable. We go over here and uncheck this. You can see this drops the weight to 0. Let's do the same for URL, as this field doesn't contain any information for searching. Instead, the URL is really only meant to be clicked on when the document is being displayed as a search result. Next, we see that we have 3 searchable text fields left: states, title, and description. They each don't really have the same importance for a user. For example, if I were to search for mountains, I would really want parks that have the word mountains in the title to show up at the top. So let's weight title the highest with 3. Now, as I change this, you can see the scores are actually changing here live on the right side. Let's also increase the weight of states, as if I search for a name of a state, I probably want only parks in that state. So now that's all that there is for weights. Now we can talk a little bit about boosts. Boosts are only for non-text fields like numbers, dates, and geolocations. You can add multiple boosts to a field, and they all have different ways of calculating how much score to add to a document. If, for example, we wanted to score parks that receive a lot of visitors higher than parks that don't receive as many visitors, we can add a log multiply boost to the visitors field. Let's do that right now. We add boost, functional boost, logarithmic multiply, and you can see that the field is being highlighted because it's being calculated now. Once we're happy with all of our changes, we can hit save and make all of our changes take effect. Immediately, searches being made with the API will be ranked differently than before because of our changes. Let's now look at a query that gets some poor results. We go to our query tester and search for biggest park. We can see that the #1 result isn't the biggest park. The biggest park is Wrangell St. Elias Park. So let's fix that with a curation. If we go to the curation tab and create a curation for biggest park, and then we can see the exact same query results that we saw previously. So if we want to add a result for Wrangell St. Elias, we'll add it here and we'll select promote this result. This means that if you search for biggest park, this document will always be on the top. We can also hide results. So for example, the Hot Springs is a relatively small park. We're going to select hide result. Now, if we were to go back to our query tester and then search for biggest park, we'll see that Wrangell St. Elias is the top result. The final tuning method is to create synonyms. So this method is fairly simple. You're basically creating a set of words that all mean the same thing. Let's take the example of bison and buffalo. If we search for buffalo right now, there's only one result because not a lot of parks actually have the word buffalo in the description. But I know for a fact that there are a lot more parks that have bison in the description. So let's create a synonym set. I close this and then I create a synonym set for buffalo and bison, and then hit save, and then go to the query tester. And now I search for buffalo. You can see that there's a lot more parks that have bison and buffalo, and so this is a lot better search experience. So that's really all there is for tuning search results in App Search. You can check out example number 7 on how to use the Enterprise Search Client to do the exact same operations that we just did using the API. All right, so that about wraps up the workshop presentation. I'm really excited to see what great things our community will create with App Search and Python. App Search has a ton to offer web and backend developers, most importantly, a refined and complete toolset for creating and maintaining search experiences for users. If you haven't checked out the code examples and demo Django application in the workshop materials, maybe give them a try. And if you had questions, you can ask me in QA or you can reach out to me elsewhere on the internet. Thank you all for attending and have a great rest of your day.